Let's look at one more problem. The graph shown here displays the area y in square feet of rectangles that have a perimeter of 200 feet and a length of x. So we're talking length times width, and as our length increases, our width would have to decrease to keep a constant value of 200 feet for a perimeter. And you can see that our area is a parabola. The first thing we want to do is interpret the meaning of the vertex in this situation. So our vertex is here at the peak. We have a length of 50 feet at that point, and the area in square feet is 2,500 square feet. So that's definitely our maximum area. And so the maximum area is 2,500 square feet, or feet squared. And that's going to occur when the length is 50 feet. So we can see that as we read from left to right, we're increasing in length from 0 all the way to 100. Now, an interesting side note to this, I know the problem doesn't ask for it, but you'll recall that area is equal to length times width. So if we have an area of 2,500 and we know that our length is 50, we can solve that our width is also 50 feet. So in other words, the maximized area when we get 2,500 square feet is when the rectangle is a 50-foot by 50-foot square. Remember that squares are rectangle, they just have all sides equal instead of pairs of sides equal. The next thing that we're asked to do is write an equation of the parabola, and I actually have lots of choices here. I could write my intercept form because I see that I have the two x-intercepts and another point. I could use vertex form because that other point happens to be my vertex, and I could use one of these values for my secondary point. The other thing I could do is I could use standard form and put these 3 points into Desmos, because 3 points on a parabola will define a parabola. So let's go ahead and look at all 3 forms. You would only have to do one that's specifically indicated on a practice problem on a homework, but I want to show you all 3 on this one. So let's start with intercept form. So intercept form says that y is equal to a times x minus p times x minus q. Now, my p and my q are 0 and 100. My x value for my random point is going to be 50. So let's take a look. Y is 2,500. I don't know a yet, but I'm going to solve for that. My x value when y is 2,500 is 50. And my p value is 0. My q value is 100. Simplifying this a little bit, I get 2,500 is equal to a times 50 times negative 50, or that 2,500 is equal to let's write our coefficient first. 50 times negative 50 is negative 2,500a. Finishing this off, even though we were working with really big numbers, we can see that a is actually just equal to negative 1. And we can write the intercept form of our equation. Y is equal to negative, we don't usually write the 1, x minus 0, and x minus 100. We can simplify this a little bit because we don't normally write an x minus 0. That would simplify to x, leaving us with negative x times x minus 100. We can also write the equation of our parabola in vertex form because we have the vertex and we have a couple of points here, either 0, 0 or 100, 0 that we could use to solve for A. However, A is always the same no matter which format we use. So because I already did the math in my intercept form, I'm not going to redo it here. I know that my A is -1. Again, you could have used the vertex and one of these points as my random xy point to come to that same conclusion. So remember that A is the same for all forms of the equation. So plugging in an A of -1 and plugging in my H and K of 50 and 2500, I could write vertex form to be negative x minus 50 squared and then plus 2500. Finally, if we look at standard form, we need 3 points minimum in order to define a quadratic function in Desmos. And notice that we happen to have 3 points. So I'm going to use these x and y values to create a table in Desmos and write my equation in standard form, just like we did with the last example. Putting in my 3 points into a table in Desmos and asking Desmos to do the quadratic regression for me, I get an A value of -1, a B value of 100, and a C value, well, we're just going to call that 0. Anytime you have something times 10 to the -28th, it's effectively 0. Using the information from Desmos, we have that y was equal to -1, but we don't usually write the 1, so negative x squared plus 100x. Part C asks us to predict the area of the rectangle when the length is 2 feet. So remember that length is our x value. We could plug into any of the 3 versions of the equation that we wrote above. Maybe seems like the standard form might be the easiest one. So I'm going to say y is equal to negative 2 squared plus 100 times 2. Remember that the 2 needs to go in parentheses because we're substituting it for x. This gives me -4 plus 200, or a y value equal to 196 feet squared. Finally, Part D asks us to compare the average rates of change in the area from 0 to 50 feet and 50 to 100 feet. The rate of change is just the slope between the points. So let's take a look at our graph here. And if we start at 0 and head towards an x value of 50, we want to know the slope of that line. And then as we move from 50 to 100, our average rate of change is the slope of this line between those 2 points. So we're going to use our points in order to write the slope of a line that connects them. So the endpoints of my line between the x values of 0 and 50 are 0, 0 and 500, 2500. I can identify these as my x1, y1 and my x2, y2. And remember that the slope of a line is just simply equal to y2 minus y1 divided by x2 minus x1. That should have been a subscript. And so I have 2500 minus 0 divided by 50 minus 0. That gives me an m value of 50. And the units on this, remember that we had feet squared for our area and feet for our length. So feet squared per foot. We can do the same thing with 50 feet to 100, again identifying an x1, y1, x2, y2, and plugging into my slope equation. I'm going to have 0 minus 2500 divided by 100 over 50, and that gives me a slope of -50 feet squared per foot.